this is a bit of an odd plot. It doesn't actually deal with the diode. It's just a triangular waveform. Isn't that right? The 920 in my book just has a triangular waveform. Is that what you're talking about? This is not even really a diode problem because it has no mention of any kind of diode. I'll go through this very quickly. This is a simple math problem, actually. For this one, I forgot the extremes, but it goes from 0 to t, and it's repetitive. It's got a peak value of a. And it's like this. This keeps repeating. Here it has a peak value of a value here of minus a. You can call this y of t if you want. Then you can call this time t. Here's period t. This would be t over 4, t over 2. Right here would be t over, or 3/4 t, sorry. But does everybody follow me on this? This is a standard waveform. It's a triangle. And he's going to, the questions are meant so that if you see this waveform, you can do half wave or full wave rectification on it, and you can get the actual peak value out, the value of A, by doing rectification with proper capacitors used. So anyway, with this one, the first thing he asked, and you correct me if I'm wrong, this is a math problem that has really nothing directly to do with diodes. Based on your knowledge, what is the average value of that waveform? What does average value mean? By definition, just tell me. You're right. Average value of the waveform, I'll call it y bar. That's a lot of times a bar means an average value. It's just what? Well, it's 1 over, say, it has to be periodic to talk about an average value. If it's anything that's random in nature, the average value has no meaning in the closed form sense. It would be a statistical average value that has to do with really like statistical noise and stuff. But it would be 1 over t, technically the integral from 0 to t of the function y of t, dt. And you all agree with that, first of all. You just integrate the function over the range, it exists that, and divide by the range, or divide by t. How many understand that, right? By looking, what is it? You're right, it's 0, isn't it? Isn't the area above the curve the same as the area below the curve over one period? So it's 0. So the first part of that is the first part of the question, isn't it, for 920? Average value? Anybody want to help me out here? You didn't? Isn't that right? Average value is 0. Right? Part A. Y bar equals 0. Now, what's the next part? We're going to do something. And so then this part 2 of this is, if it is half-wave rectified, plot the voltage versus time and determine the DC value. Now this is half-wave rectification, so here's what he means by that statement. All the negative going parts you get rid of. Y'all hear me on this? So it's this. Just look at one period. I'm going to get rid of them all. Remember, that's the period t. So really, it's 0 for the first part. Now, take a look. What's the average value of that? It's got positive area. Do you agree with me? What is the actual area under this curve? This would be t over 4, t over 2. Well, technically, you would integrate this, right? And then divide by t. Do you all agree with that? In other words, this formula still applies, but now this is a rectified waveform. Call it y sub r. All right. What's the area under here? Isn't it really just a times t over 4? Right? How many see that? And if you divide by t, it's just what? A over 4. Do you all agree with this? Give me a show of hands if you do. I'm being a little casual with this because it seems very obvious. So this part B, the average value of the rectified waveform would be A over 4. Now, that is not full wave, but half wave. The final part of this, and I wish he would have drawn these waveforms. If the wave, what does it say? If the wave is full wave rectified, plot the voltage versus time, calculate the DC value. Now this, just listen to me. Full wave means the entire waveform is going to be in the positive sector. The negative going parts will become positive. Y'all with me? And it looks like this. Can everybody follow me on that? Now, if you just look at this, can you see now the period would be T over 2? Just let me see your hands if you can. It repeats itself over T over 2 instead of capital T, right? That's, the period is always the distance in time, or whatever the horizontal plot is based on, over which the function, the vertical axis, or dependent variable repeats itself, and for any periodic function that's true. This one over T over 2, so what is the average value of that? By looking. Well, it would be A times T over 4 would be the height. Do you agree with that? I mean, that would be the area under that curve, correct? Just under this curve. And it would be divided by T, cap T. So it's really A over, did I say A over 4 for that last one? No, sorry, I'm sorry about this. This would be A times T over 4 divided by T over 2. Sorry, the period changes there. Or it would be twice this value. So for part C, the fully rectified value of this would be A over 2. Do you agree with that? Is that what he has in the solution? He'll have some form of that.
It says AT over 2.
Yeah, that's the last part. That's fully rectified. The only thing he's doing is mathematically, he's asking for mathematically what the values would be. Has nothing to do with the diode in a direct sense, but you can easily achieve that, and I'm going to show you how. If that waveform, say this was the voltage waveform that we started with, and this is kind of important because some of you are going to have to be analyzing some sorts of circuits that will actually do this kind of thing if you're in any type of energy scavenging group. Here was the waveform originally. It just keeps going. This would be T. So if that was the waveform, then that would be a voltage waveform, and I'll call it V of T here. And I let this V of T be here. And then I put a simple diode like this, make it an ideal diode too. And I put a resistor here. Then this output, if I call this V out of T, you would get the rectified waveform. You would get this. This would be A, this would be T over 4, this would be T over 2, this would be T. Can everybody follow me on that? The reason is the diode only lets current flow this way. When that current flows, there's no voltage drop. All this voltage appears here. Follow me? But when the current tries to go the other way, it can't. So no current, no voltage. All the voltage would be across that diode. And therefore, the negative going part of that waveform would be X'd out. Y'all follow me on this? Just let me see your hands if you do. I want to make sure you see it. You guys see it or not? I want to make sure. Yes or no? If you don't, I'll go into more detail, but that's the simplest possible half-wave rectification circuit. Now, full-wave rectification, it's a little more involved, but it's the same basic principle I'm going to show you. Consider that waveform still. Here's what full-wave rectified circuit would look like. It's important you actually appreciate this and understand it. So for full wave rectification, we're gonna put the voltage just as before here. That's the V of t that I'm showing you right here. Then we come to this point, and what we do, we're gonna have all the current flowing to that point, and no current flowing to this point. So if you took these, if I took this, and I'm trying to do this in a decent way. Y'all follow me on this, guys? I'm just gonna go through the operation, you'll see it. Here's what the V of t would look like here. V out of t. Now, follow me. Let's assume it's positive for now, right? Current wants to flow this way. Can you all follow me? Everybody with me? It can flow that way. Do y'all follow me? It can't flow that way. Got it? Wants to flow that way, flows into here. You'll notice at this point, it flows and hits this point. Now, the thing about this is negative here. If a current can't flow this way, if that's negative, y'all follow me? It would want to flow this way, but it can't. Y'all, so it can't flow that way, right? It can't flow that. Matter of fact, only current can flow into this. Now follow me on this. So when it comes down through here, and it would cause that to be plus minus and goes over here, then it can get back to the negative going through that diode. Does everybody follow me? Let me see your hands if you do, please. Just tell me if I'm getting through to you, because if I am, I'm not gonna waste a lot of time on this. It's obvious if you think about it. With me? Did you have a question, sir, or just agreeing with me? You agree? Okay. Now, what happens when the other thing happens? So the first part of this basically shows you this waveform does this, right? It's just gonna track the positive going half of this waveform. Now when it goes negative, this isn't hard, just think it through. When it goes negative, when all of a sudden the polarity is this, right? As such, correct, class? Can you all see it back there, way back? Man, you're almost hidden under that laptop screen, but you can see it for real, okay? When it's negative, it comes down here, right? It can go through this one, but it can't go through this one. So it comes this way. Now it's still coming out. You can label that positive and not the negative terminals, but this is full wave rectification in essence. Comes down here, right? Hits this, comes down. It's still got the same polarity, plus to minus, and then it returns, but it returns this way. Can you all see that? So two diodes are always on, and that's called a full wave bridge rectifier, and two diodes are always off. Except at the transitional point where it goes through an absolute zero, then nothing's on. Y'all follow? That's it. This is an ideal. So the waveform coming out of this would look like this. And if you're just a little more detailed, and I think I can basically, you can handle it from here. What is really done in the world, the real world, with these things, because obviously this is not a DC signal, even though it is strictly positive, right? You all with me on this? So what they'll do is this, to make it a very flat DC waveform, they'll take some, I call them ginormous capacitors, but they're basically going to do this. They're going to put a capacitor here, and they'll put an inductor here and a capacitor here with respect to ground. Now, hear me on this. This is the side that's always positive. Y'all follow me? What these do, when they charge up, that inductor, first of all, is going to slow down any kind of fast transitions. Y'all with me? That capacitor is going to charge up and it wants to maintain the voltage on there, and it's depending on what the load is, R, but this inductor slows it down, and then this capacitor gets rid of any additional, it's called ripple voltage. So the output waveform, once you do rectification, is basically going to be just the DC value of that thing. And you'll see in schematic diagrams, some of you are going to have to do energy scavenging and all that. I didn't even know, but the actual electric motors on cars are three-phase. One of my students gave a presentation yesterday in an electromagnetic compatibility course, and a lot of MEs are going to be working in Detroit for General Motors and Ford and Chrysler with energy scavenging. This is for hybrid cars. Y'all follow me on this? Those batteries, and with electric vehicles, are actually three-phase motors, at least the ones he's working on is. Three-phase is something we covered. They're AC motors, not DC. Y'all know the difference between AC and DC motors or not? Did you have this in your machines? What course did you get in it? Just you know it? Does anybody else, did you have it in any course? You have something to do with rotating machinery in your ME courses, don't you? Or not? You didn't take it? I know you will in aerospace, but I'm just not sure where. There has to be some, when you get into this stuff, what I'm trying to do, they always recommend, since this is an applications course, anything that would apply directly to people in the real world doing energy scavenging or something like that, you're supposed to mention. I'm telling you right now, that type of a circuit you'll see in energy scavenging courses, or energy scavenging systems at Detroit, if you go there, or anywhere else. And I don't know how many people in here are going to end up working for one of these automobile companies, but my students are working up there, and they have lots of MEs from Auburn University they're working on all aspects of cars, not just electric vehicles and hybrid vehicles. I'm sure they're dealing with the next generation internal combustion engine too, but we got a lot of people up there doing EV work, because that's supposedly, after Elon Musk and his Tesla, that's sort of the next revolution in the automotive industry. Is going to be some very efficient long-range vehicles. By the way, how many have been in a Tesla? Was it a self-driving Tesla or not? Do you know what I'm talking about? They now have, and this blows me, and this is several years back, this person lives in Georgia, got in the car, the Tesla, and it drove him to his place of employment here in Auburn, and then drove him back. That's pretty futuristic. I don't know if I feel comfortable with a car driving me without me driving the car. And then that crazy Tesla that looks like an armored vehicle, that's what. Next generation combat. All right, I want to do a diode problem before I move on. So I'm gonna, you won't pick one, I will.
That's true. That happened.
And they're like 6 inches.
It's like a ram.
It's like a higher camera. Just in case you can't see anything, you need a higher camera. Yeah.
All right, I'm gonna do 921. I believe that was a sign. How many tried 921? I'm just asking. Nobody? What? What's up?
I don't think it was a sign.
Was it 21 a sign?
No.
Well, it's a sign now. It will be. All right, so this is 921. And I'm going to show you the differences in some stuff. So part A is ideal diodes. And here, this is, by the way, what's the name of that Tesla that looks like an armored vehicle? What is it called? What?
The Cybertruck.
Cybertruck. I gotta remember that, because I'm having conversations about this crazy vehicle. If somebody owns one, it's not against the vehicle, it just looks futuristic. All right, they say V1 is 2 volts. In part B, V1 is 8 volts. So we're assuming ideal diodes, we got V1 equal to 2 volts. Now, just reason it through. Try this one right now, just mentally. Force yourself to do this. Find out if you understand this stuff or not. If you don't, hopefully I can help you. All right, when you have 2 volts here, this is the way I recommend you do a problem like this. There's parallel legs here, right? Get rid of one of them in your mind. Disconnect this part. We're just going to allow this part. We want to see what happens. Y'all follow me? We're going to do this the smart way. We're going to go through and break it up into possibilities. And the possibilities in terms of diodes are they're on or they're off. There are 2 diodes, therefore we have 4 possibilities. They can both be on, both be off, one on, one off. The one that was on is off, the one that was off is on. Follow me? There's 4 possibilities. This possibility right here, we can look at 2 of them. Either this diode can be on or off. Do you all agree with that, first of all? Think it through, guys. If this was on, what would have to happen? Current could flow this way. That would be happening, right? Now ask yourself, can it? Well, if current flows this way, you're going to have a voltage drop here, right? Then there's no voltage drop here, but there's another 2 volts drop there. Well, 12 is greater than 2. That one can turn on. Do you agree with that, class? Everybody follow me? All right. So if that circuit wasn't added to this circuit, this thing could turn on. Furthermore, listen, if I ask you the voltage between here and here, what would it be? Think about it. Is there any voltage drop across that diode if it's on? Class? What would the voltage be between that positive and negative terminal here? Class? Just 2 volts, right? It's going to be that V1. You all see that, far back especially, because you guys have worked about it. Y'all with me? Okay. So it'd be 2 volts here. Now, hear me. We're going to skip a few steps. Normally I would go ahead and say disconnect that, connect that one, see what happens. You're going to find out there's 6 volts here. I'm going to tell you that. Well, then you do some rational thinking. If there's 2 volts here and you put something down that says 6 volts, well, if you connect them, it sounds like current would have to flow this way in order to neutralize that. Do you all follow me, class? Give me a show of hands if you do. Is that allowed to happen? No, if you hook these 2 together, what that means is this diode is off. How many see the rationale for that? You guys are out here, or you see it or not? Now, there is something, if they're both connected and you're going through this, remember the possibilities. Both off. Can they both be off with this circuit? No, because current can flow through one of them for sure. You'll know the 12 volts will overcome the 2 volts or 6 volts. You all follow me? All right. So then you go back down and say, well, if this one is on, what happens? I would have 2 volts there. That is a possibility. If I had 2 volts there, would anything flow in this circuit? Zip, right? Y'all with me on that one? It can't. I can have 2 volts here, right? But for current to flow this way, I would have to have greater than 6 volts here. Do y'all follow me, class? I want you to think that through. Now, if you want to really, if you really want to see everything, just erase that and put this one here and see what voltage would occur there if that circuit was there. What would it be, class? 6 volts, right? But then you put this one in, and it would go down to 2 volts. Y'all with me? So we would have, for that part of the output, it would just be 2 volts. Now back to putting this one in. All right, these are both ideal right now. I'm gonna leave my ideal for the, I wanna do the next part B. Do you have a question or? No, okay. If you do, just yell. But for the second part of that, it says, what if V1 is 8 volts? Now, this is a good question. What happens when V1 is 8 volts? I want you to think it through. Some people probably see this. What did I just do effectively? I did what? I put the larger potential voltage in series with the first diode. The second diode only has 6 volts to overcome. That diode has 8 volts. What do you think's going to happen? Your gut feel. What's going to be the output voltage? You're right. How many think it's 6? Still suspicious. Do you see it or not, guys? I mean, it is got to be based on the same idea we had earlier. If we take this one out, the output would be 6 volts. If we took this one out, the output would be 8 volts. Well, there ain't no way there can be 8 volts there if only 6 volts is required to turn this diode on. It will be brought down to 6 volts. Do y'all follow me? Has to be. These are good problems. It basically makes you aware of some of the mechanisms for blocking certain circuit paths for current flow. All right, with me? Now, for ideal diodes, and I want you to listen to this, the only change, for non-ideal diodes, the only thing that changes is now you're going to have to overcome not just this voltage that's here and here. I'm going to leave that at V1. But for non-ideal diodes, now you're going to have this, but there'll be a potential of plus to minus would be V diode here, and right here too, there would be plus to minus V diode. And I'm just going to ask you this. For this situation, we'll go back to the 2 volts here. We remember in the beginning we said, well, the output would be 2 volts if that was connected and they were both ideal and V diode was 0. Do you all agree with that? All right, with V diode, whatever it is, he's going to say 0.3, I think, and 0.7 volts. Just want to make sure. Oh yeah, then he says Schottky. Don't worry about Schottky diodes, that's a special application. For 0.7 volts. So then if V diode is 0.7 volts right here in both of these, the only thing that happens is now it won't be just 2 volts, it will be 2 plus 0.7, or this would be 2.7 volts. Do you all follow me on this, class? How many see the idea and understand? It's not hard, but you have to be attentive here. You can make mistakes by not understanding this stuff. Base level understanding, and I'm just leveling with you. That happens all the time with diodes, especially when you got a million other things to do. I've got a test in this, a report due. Who knows? I got to go buy groceries because I can't starve. Stuff like this, it'll get in the way of this. Please try to be focused when you're in here. I'll help you. With me? Okay. Now, there is another part to the non-ideal diode, and that is when they give you a resistance, a small but measurable resistance to put in series 2 with that. I don't plan on doing that, but that's something to be aware of in the long run. If you ever have to work with these circuits for laboratory work with diodes first, that will become an issue. And if you want to get any of this information for real diodes that you're going to use, they have data sheets. Any diode you buy, there's a data sheet for it online, and they will have this information very clearly shown. Y'all with me, class? I'm just trying. Has anybody here built stuff with diodes at all? Just wanted for any laboratory work? Nobody? I know you guys are gonna use op amps. I know that. You're gonna use programmable logic controlling circuits, right? PLCs, don't you guys do that in some, I don't know what lab you do. You're gonna use all the modern electronic stuff that's cheap, that's used everywhere for you. All right, so this, I'm just going through this. Wanted to make sure I talked about that before I get into the next stuff, which is bipolar junction transistors. Now, this is, I believe, in chapter 12, and I've got to make a statement here. When I talk about transistors, I'm talking about something that a guy named William Schottky long ago got a Nobel, I think he got a Nobel Prize, but he was supposed, he's credited as being the inventor of the transistor. It's really, it was a bipolar junction transistor. That's the type we're going to study. This is a long time ago. I think it was in the late 50s, early 60s. It changed the world, you might say. It brought in the computer revolution, high-speed computing, very large circuit, very large integrated circuits, or very large system integrated circuits. Basically, your phone is an after product of that being available. If we were still using vacuum tubes, you could forget that phone. You could forget 99% of everything you have that's electronic. So it was quite an important advancement. It changed the world. The type of transistor that he figured out is called a bipolar junction transistor, which we will be studying. There's a second type. It's called a metal oxide semiconductor, a MOSFET, or possibly even a JFET. I don't want you to worry about that. The operation, they do the same thing. The MOSFET is a little better at a lot of things because it's lower power, but the bipolar does everything, and it's a little faster, so it's used a lot. Do you know what TTL logic circuits are, by any chance? Just asking questions, because you do? All right, transistor logic, those are things that are based on bipolars. They're fast as heck. All right, so what is a bipolar transistor? This is called a bipolar junction transistor, or a BJT. Just write this down. I'm going to give you the Cliff Notes version that you need. Not a lot of solid state physics that you don't need. I don't think you want me to go through that for diodes. I know you don't, because you'd get something that would be an exponential relationship of the output or the flow current to the actual input voltage, and you do not need that. So what does it look like? This is the symbol if you look in chapter 12 for it, and they'll have an arrow down here. Now that sure does look like a diode. In fact, it is a diode. This is called the emitter, this part of the transistor. But what you'll actually see is this. You'll see that thing with a circle. If you actually go to bind, you're going to see this. This point of contact here is called the emitter. And the current will flow out of this one. It's called IE. It's the emitter current. This is called the base. And current flows into the base. Whenever you see capital letters, they denote a DC, or continuous current. And you see a small IB or small IE, it has to do with AC current. Bless you. Then you're going to have a current flowing down here, IC. This connection point is called the collector. That's what they look like. And what this is a voltage controlled current amplifier. I'm just going to tell you this. The voltage between here and here, this is the base and this is the emitter. So the voltage between the base emitter, or VESA, BE, dictates the current that will flow IC. Now here's some important relationships that are continued, that will be true in what's called the active region. There's a lot of information that I'm going to develop the definition for as we go. I can't do it all at once because there's certain things that are defined in terms of each other. It won't work. So you're going to have to just follow me. So if we are in, and just for now, just call it the active region. this is true. IE is equal to IB plus IC. One look at the way I drew it, it makes perfect sense. What goes into has got to flow out of. It's basically Kirchhoff's current law. The second thing is that IB is equal to something called beta, or I'm sorry, IC, my bad. I sub C, the collector current, is equal to something called beta times IB. And this is important. Now, beta's typical values are of the order of 100, but they can go up to 500, 600. That's called the current gain of the transistor, for lack of a better way of defining it. All right? And you could obviously take that and stick it in that equation, and you get IE is equal to, well, if you look at this, you would have IB here plus IC, or you would have 1 plus beta times IB. Now, for all intents and purposes, for large values of beta, like 150, 200, I collector and I emitter are about the same. 100 times something versus 101 times something is about 100 times. With me? Just keep that in mind. You're going to see at some point in time, you're going to be dealing with systems that have these for what are called controllers. And nowadays, see, my real problem is, in the old days, when you had engineers working on engines, energy scavenging, even internal combustion motors, the people that worked on them, they knew all aspects of electronics, they knew all aspects of mechanical engineering, they understood strain, stress, torque on the motor, how to get, basically the entire four-stroke cycle system. They knew exactly how to calculate efficiency. Nowadays, it's more compartmentalized, but still, with energy scavenging, which I know MEs are going to work in this area, I just don't know how many. You're going to see this transistor. So I'm going to try to tell you, what I'm trying to tell you is, you're probably going to see it at some other point, some of it, if you work in that area, not everybody. I can't really tell the aerospace engineers or IEs they're going to see this. They might, but anyway. So this is the equation these are the equations that dictate the current relationships. Now, the best way to do this is do some problems, but I got to set it up for you. So the next thing you take a look at is this, and this is called an NPN transistor. So why NPN? Here's why. The material, there's a good picture up in your book, but they're going to show you this. This is actually the way it would be made. There would be a small amount. This would be a silicon, a bar silicon, and I'm doing it in a very basic way. And there would be something here that's called a diffuse junction that would have N-type dopants. It means there are more free electrons in what I consider the conduction band. You all had material science, right? I mean, you had whatever you call it, materials engineering, materials. So you know about the band structures in solids, right? You know that there's what? A valence band. Those are electrons that you can't bounce up there to the conduction band very easily. It takes a lot of energy. And then there's what? The conduction band, like in metals, there's a ton of free electrons. It's like an electron soup that can move. Did you have this in your classes? I don't know how the professor explained it. Yes, you did? Or not? What class was it?
I have a materials minor, so.
Oh, okay. Now, I hope everybody's had some exposure to this. It's very basic, and I'm doing this very simple. I'm not going to go through K-band diagrams or anything like that. So there's N-type material here. Then it's surrounded, and this is all done by diffusion, where when they form this, the first thing they do is form the base. They diffuse a P-type material right there, but the density of the P-type is much less than the N-type for the emitter, and they diffuse this thing in there by putting a mask on the upper part of the transistor. It's basically like a photoresist, and then they expose a certain part of the resist, they get rid of it with some distilled water or something like this, and then they put a dopant in there under high temperatures and drive it in. It diffuses very slowly. We cause a base, and that's just all you need to know. Then below this, outside this whole thing, there's the collector, and there's usually a contact point for the collector, a contact point for the base, and a contact point for the emitter here. This is the emitter, base, collector. Now, so how does it work? If I was explaining this to a bunch of high school kids who were, say, sophomores, I would say this. First, they have to understand the basic problem with PN junction diodes, that there's a gap here, a natural gap, where because of the way the actual band structure is, you're going to get a vacancy, a bare region there, that the only time you're going to get any current flowing is you've got to make that basically this distance go to zero by putting a forward bias. Now, if you think about it, this is an NPN transistor. So if you had just basic diode theory, if you had N and P and you wanted current to flow, it couldn't flow this way, but it could flow this way from positive to negative if there was a certain voltage, say, base emitter exceeded. Remember how in diodes, non-ideal diodes, you had to overcome 7/10 of a volt for anything to happen? That's why, because the bands basically have to be bent. Oh my gosh, this is beyond what you need to know, so that current can flow. That's all this is. It's basically an electrical potential that happens internal that you have to overcome. And this right here, you can put down, you might as well think of as a diode. This junction from here to here, it looks almost like a diode without that straight like this. Follow me? That blocker there. So that's a diode, but it's non-ideal. It always has, they'll call it V base to emitter, or V on, something like this, or V diode, or V on. Don't worry about it. It'll be about 7/10 of a volt. Almost always 7/10 of a volt for silicon at room temperature. It is dependent on the type of material. Gallium arsenide is much different. Have you heard of gallium arsenide transistors? Or germanium? They are much different. Germanium is much less, and I forgot what it was, 0.3 volts. Gallium arsenide is a 3,5 compound, it's different too, but for now we're going to say 7/10 of a volt. So the best way to see this is a simple example. Listen to me. And I've got a good one. How this whole thing works. By the way, if you want to write this down, please do. It'll help you get a better idea. Page 355 has a cut-up view of the cross-section of an NPN. That's on page 355. And then on page 361, I'm going to go through this problem in there, but I'm going to do this in a way that is revealing of all the basic information, how it applies to a solution to a problem. That's what you really need to see. How does all this apply to any kind of problems I might be exposed to or see? So pay attention to this. This is on page actually it's 360. So they have a source of 6 volts. It's DC. And then they have a resistor here of 285. What I'm going to do is actually do this generically, and I'll show you what line. Then we'll add the values. we're just gonna call this VB, and we're gonna call this RB. And it's going to be connected right to this bipolar transistor. And then there is a resistance of, he calls it, this is the collector. Remember, this is the emitter, base, collector. Now there's going to be a collector resistance, which I'm just going to call RC. And there's going to be some voltage here, which I'm going to label as VCC. And ground it, and I'm going to ground this one. And what we're going to do is use what I told you before, where I just put down for the first time in a real problem, but I'm doing it with just arbitrary values. I want to say one other thing. The beta of this transistor will be given. It will become 100, but I'm going to say 100. I'm going to use 100 right now so you can see the relative sizes of these currents. I'm going to say the actual V base to emitter on voltage, and call it the on voltage, is 0.7 volts. All right. Now, we're assuming VCC and capital VB are much larger than 0.7 volts. Here's what happens. First, the way you always do this is you want to take a look at the base current here that would flow. Y'all hear me? This is real important. I'm almost out. So to model that, you would have plus to minus V base here. You're going to have the base resistor. This becomes the non-ideal diode. If everybody follow me this, I know I'm about out of time, I probably am, but just bear with me. I'm trying to do you a favor. So now I need this current, IB. Can everybody follow me? That's the ideal diode. If VB is greater than 0.7, is it on? Class, how many say it is? I just need to know, all right? So now I can say that IB itself can easily be found by taking VB minus 0.7 volts over the resistance RB. How many see that? This is direct. Nothing new at that point. Now, if I have IB, I automatically have IC, which is beta IB. How many see that? Beta is 100, I said, right? If I know IB flowing, and it flows in this direction, I also know the voltage across this, don't I? That would be IC times RC. Do you everybody see that? So this voltage right here, which I'll just call V sub small c, is going to be IC times RC. If somebody's in this class is calling me, I'll get you. All right, you with me on this? So the question that they would like answered is, what is the voltage between here and here? Just tell me what this VCE is and why. I bet you know. Listen, if I want the voltage from here to here, start at this terminal, right? We start here, that's where the negative is on this plus to or minus to plus, right? Go around, I get an increase of VCC, and then I get a voltage drop of that small or IC. So I can say, just write this down and you're out of here. VCE is equal to VCC, whatever it is, minus, and here it's going to be IC, which is just beta times IB, and IB is this, IC times RC, and in fact that's it. Now we've gone ahead and we've calculated everything but the emitter current. You want the emitter current? Just add the collector and base current together. That's it. I'll give you some homework on this. The quiz on Friday will deal with the diodes. But do these, who knows?